everybody, and welcome back to the channel and to the series, or if this is your first time here, welcome. In today's video we're going to be building a variety of CRT shaders, ranging from the Shadowmask layout used in computer monitors, to the Trinitron layout used in very early TV displays, and then later replaced by the Slotmask technique, and finally, a technique of my own design, which I have named Slice-A-Pie Pixels, which as you can see is so named because it behaves exactly like a pie chart or a pie graph. To follow along with this video, you'll need some custom nodes, namely the UV grid node, the UV brick, and the UV profile, and some utility nodes, the UV distance node, the fader, and the value mix node. If you've been following along with the series so far, you should already have those nodes. If not, you can pick up those nodes ready built for you and ready to go from my Blender Market page. Look for the UV Grid Materials Pack. You have the option of downloading the Nodes Pack or the Complete Materials Pack if you don't have time to follow along with the series. In the Nodes Pack, you'll find all the nodes you need to follow along with this video and all the videos of the series. And the Materials Pack includes all the materials I have created or will create throughout the entire series. The CRT, or cathode ray tube, was an old technology used in visual displays, TVs and computer monitors and the like, then to be replaced around 2007 by flat screens like LCDs and LED panels. And CRT displays are very easily recognized by their particular pixel layouts. There are a few different types of layouts. This one is the Shadowmask layout used in computer displays. For comparison, this is the Shadowmask layout used in a PC CRT display, compared to a Slotmask technique used in TVs. Here's a close-up of the Trinitron layout, and you'll notice a few peculiarities of the layout, namely a little space, a little mask between each individual color column, so each red, green, and blue column, and then each triad of color columns has a slightly larger border between it and its neighbors. Another peculiarity of the CRT display is the way in which the image gets refreshed, illustrated very well by this little GIF right here. This is the interlaced method of refreshing the screen. This happens many hundreds, possibly thousands of times per second, and this is what creates that characteristic flickering of a CRT display. So with all that information, let's come back to Blender and get down to building some materials. For this tutorial, I'll be working in Blender version 2.83. If you're currently using a later version of Blender, all the nodes and operations that I use in this tutorial will be available to you, but some things may have been moved around and some names may have been changed. If you can't find any of the nodes or operations that I use, check the Blender manual or possibly just try a Google search for the operation name or the node name that I've used and your current version of Blender, and I'm sure you'll find it. In terms of my layout, I'm in my shading workspace, which consists of a very large node editor window. I have a timeline editor down here for any animation that I might be doing. My preview window is a simple 3D view up in the top right here. I have a plane sized 1 by 1, and I'm looking at that plane from the top view. I keep the overlays turned off, and down in the bottom right I have a properties panel and an outliner window. Here I have created a new material and I am ready to begin with a UV map node and a UV grid node. As you can imagine, in a lot of these materials, in essentially all of these materials, we're going to be pixelating images. So I'll drop in an image texture, I'll use the stepped output and turn step correct on. Now I'm going to choose a photograph of a person. I'll go to preview and there we go. Since we're in Eevee, I'm going to change texture interpolation from linear to closest to remove the borders. Now I'm going to drop in some value nodes so I can control the width and the height of my pixels. I'll go to the width and the height of the UV grid. Now I'm going to create two utility nodes, which we're going to need for essentially all of the materials we're going to create today. The first one will be a way to take each pixel of the pixelated image and divide it into the three components of the color of that pixel. Then we'll assign the red, green, and blue values to columns, which we'll assign to the left, center, and right of the pixel. The second utility we'll have to create is the refreshing function, which will be present in all of the shaders, but we'll see that in just 1 second. To go about dividing each pixel into three columns, I'm going to use a separate RGB node, the normalized output, Let's have a look at the X. And now with some math nodes set to greater than and less than, I can create masks for sections of the gradient. Each individual gradient goes from 0 on the left to 1 on the right. So if I use this greater than node with a threshold of 0, it gives me all white. If I increase this value, you'll see that the size of the mask actually gets reduced, as now the mask is giving me from 0.66 to 1. So if I get another math node, I'm going to change the operation from greater than to less than. This one I'll set to a threshold of a third, 1 divided by 3. And now I can multiply together these two results. And there you go, I've got my left-hand column. So this is going to be a handy function. We're definitely going to have to do this a number of times. So I'm going to create a utility node to do this for me. Control and G to create the group and rearrange the nodes so they sit well in place. I'm going to remove that reroute. And this node I'm going to call a thirds mask. I'll click the shield to keep this node, but I'm not quite finished with it just yet. The way these nodes are set to work is that they will return a value of 1 or a color of white for everything which is above 0 and below 0.333. Now that might not be exactly what you want. Usually if I set a range, if I want these nodes to create a mask for me from a range of 0 to 0.333, what I actually expect is for 0 to be included in that range and 0.333 possibly to be excluded from that range. Maybe I want everything until just before this maximum threshold, because then if we're dealing with columns, for example, let me show you what I mean. I'm going to get a separate XYZ node and separate the stepped output. I'll turn off step correct temporarily so I can get a 0 here. Now if I use my thirds mask, first of all, I should expose the threshold so I can change them from the outside. We've got two thresholds. I'll call one min and one max. Now then, if I expected to be able to mask off this column, for example, this column has a value of 0. If I want this column and nothing afterwards, I might think that I should enter masking values of 0 to the value of this next column, which would actually be 0.1 because that's the width. So let's have a look and see what I get. Nothing. And that's exactly because it's not including 0 in the range that I want. So to fix that, what I'm actually going to do is invert this operation to less than, and then again invert the result of that node by subtracting it from 1. And there we go. That's the result I want. So I'm going to change this name from thirds mask to value mask. I'll drag this one up a little bit and I'm going to duplicate it. This first mask node, I'll set a minimum of 0 and a maximum of 1/3. The second mask, I'll set a minimum of 1/3 and a maximum of 2/3. And that's what that looks like. One final duplicate, and I'll set this one to a minimum of 2/3 and a maximum of 1. And that is what that looks like. I'll hook up my separate RGB coming from the normalized output. And now I've got my left column, my middle column, and my right column, i.e. red, green, and blue. So I'll combine those columns into a color. Red, green, and blue. And now I can multiply the color output of my texture node. With a mix RGB, I'll set the operation to multiply a factor of 1 and plug the result of my combine RGB into the bottom. There we go. If I set the pixel size to something notably smaller, you'll start to see a much more pleasing result. There we go. Zoom in and you can see the colored columns, zoom out and the image gets its definition back. If I were to set the pixel size to 1 divided by 480, for example, there's a good looking image. And the columns are still there, believe it or not. Let's combine these nodes into a single node, and this one will be the thirds mask. Control and G. In terms of inputs and outputs, we're ready to go. So I'm just going to give it its name. Thirds mask. And there we have it. One handy little node, much more easily moved around, stacked, and arranged. Now then, let's tackle the interlacing. If you've seen the earlier videos of the series in which I build self-typing text and the matrix code rain, you might recognize this technique from those tutorials. I'm going to duplicate all of this setup, the UV map, the UV grid, and the input nodes. Let's have a look at what that gives us. I'll increase the pixel size just so I can see what I'm doing. There we go. Now then, we'll be using the stepped output. We're going to separate it with a separate XYZ node. And now I'll use a math node on the X component. I'll set the operation to less than. And this now allows me to sweep left and right across the gradient using this threshold. If I add to the X component the Y component, it changes that sweep to a diagonal sweep. If I then multiply the value of the X component by the height variable, I can now sweep through the rows sequentially. And I want to invert the vertical sweep. I want to sweep from top to bottom, so I'm going to invert the vertical component, the Y component, by subtracting it from 1. There we go. So now we have our sequential row sweep correctly functioning. And to introduce the interlacing, here's what we're going to do. Let's take this node, which is essentially our Y component, which has inverted the Y component. We're going to divide that result by 2. And you can see that now we have dual lines happening, which is promising. I'm going to move my less than node over to the right just a little bit. And I'm going to Control-Shift and D to duplicate this node and keep the connections, because all I have to do to this one is to multiply the height input by 2. Now I can use the normalized output. I'll separate it and check out the Y component. I'll drop onto that Y component a math node set to less than with a threshold of 0.5 and divide my result by 2. Just like I did here. And in fact, I'm now going to take that result and add it just after the previous addition. And now with my less than node, you'll see that at 0.5, I'm here essentially at the bottom of the screen, almost completing the first pass. There's the second pass. If I go backwards, you'll see the second pass get undone. There's the first pass get undone. The rows are still sequential. The gaps are correct. And we're definitely looking good here. To change this hard mask setup to a gradient fall off, all I have to do is to change the less than function to subtract. And there's the gradient. And to make the gradient loop, I'm going to add another math node and set the function to fraction. And there you go. We've got our interlaced, refreshing, looping animation happening. To change the intensity of the flickering which results from this effect, that very characteristic CRT flickering, I'm going to use the result of the fraction node to drive a value mix. That'll go into the factor. Let's preview that output. For now, nothing will have changed, but this means I can use the values of this value mix node to change the darkest and the brightest of the gradients. Most useful for changing the darkest of the gradient. If you want to increase or decrease the intensity of the flickering of the screen, this is where you'll do that. You'll see that with a value of 0, I'm getting a full range of black to white in my flickering, and so the flickering is quite intense. If I increase this value so we don't go as far down as pure black, the flickering will become much less pronounced. In fact, if I set this bottom value to 1, you'll see the flickering disappear entirely. So a value of 1 will give me a flickering intensity of 0, and a value of 0 will give me a flickering intensity of 1. So as you can imagine, I can use a value node to control this input. All I have to do is to invert it. So I'll feed the value into the bottom of a subtract node, subtract that result from 1, and that goes into the top of my value mix. There we go, an intensity of 0, there is no flickering. An intensity of 1, we see maximum flickering, and I have granular control of the intensity of that flickering. Very, very good. All we got to do now is to wrap this all up into a utility node so we can use it and reuse it. I'll group together these noodles to avoid any copied inputs when I create my node. Let's select all of these nodes, Control and G to make a group. And we'll line them up nicely. There we go. I can remove the reroutes. and I'll line up the output node right there. We're going to need a few more inputs. But first of all, I'm going to rename the inputs that we already have. Input vector will be vector. The first input will be width. The second will be height. I'm going to turn on offset correct and expose the offset function of the UV grid node, because if I have an offset in the UV grid node creating the pixelated image, I need to reproduce that offset in the refreshing. So we can turn offset on and off from the outside. We can set the width and height from the outside. We need to be able to control our intensity, and we'll need an input for this time variable right here. So I'll add an input group input, create a new input, and name it time. And I'll get a duplicate of that, drop that up the top, and expose the factor of this fader node to the outside, which I will call intensity. I can now get rid of this fader node actually with Control and X to remove the node, but keep the noodle connections. There we go. Let's have a look from the outside. Vector, width and height, an offset, a time input, and an intensity control, all looking good. So we'll name this node CRT refresh. I'll drag this refresh node up closer to the UV grid creating the image for me. Let's preview that image. Now then, I want the CRT refresh to share the input nodes that the UV grid node uses, so I'll supply its UV map, its width input, and its height. And now I can delete these input nodes, and I'll use the output of this CRT refresh node to drive the factor mix of a color mix node, mix RGB. The color result of my image goes in the bottom, and I'll set the top color to black. The result of the CRT refresh drives the mix factor, and there we go. Let's see the time. You can see the flickering happening. I'll zoom out a little bit more. You'll see it happen line by line. Increase the intensity. There you have it. Very nice. Now we can reuse these nodes for 3 of the 4 types of materials that we're going to be making in this video. First up is the Shadowmask layout used in PC monitors. Let's have a look at that. Okay, first thing, I'm going to turn step correct back on. I turned that off earlier on for demonstration, but I do need it to be on, and I'll reset that time to 0. Now then, quickly back to Wikipedia, just to have a look at the Shadowmask arrangement. Now the way I'm going to do it is to arrange the triads colors, so red, green, and blue, linearly. And so each pixel will be 3 times as wide as it is high, making room for 3 equally sized dots. And then in the alternate row, we can see that there is an offset between the red pixels, or the red dots in this case, of 1.5 dots. 1.5 is a half of 3, so that'll be an offset of 0.5, exactly like a brick wall. Before I go any further, I'm going to account for the darkening which has happened to the image as a result of multiplying the color of the image itself by the thirds mask, and then this introduction of a black background, and then this darkening of the color by the flickering effect of the refreshing of the picture. And the darkening will get worse in later versions of the shaders as we introduce masks which actually introduce a background color which will be black, further darkening the image, and so we have to take that into account. We'll compensate for the darkening with a little brightening. I'm going to use a mix RGB with the function set to divide. The bottom color I'm going to set to a gray with 0.1 for red, green, and blue. I'll drop that between the multiply and the mix, and now this factor is very simply a brightness slider. If I preview the original image, that's the brightness. Take note of that, and then we'll look at the modified result. I'm a little too bright now. I'm going to reduce it a touch. There we go. That's looking pretty good. Okay, I'm going to increase the size of the pixels so I can actually see what I'm doing. 0.1, I'm going to make them very, very big. And as you can see, each pixel has been split into 3 columns. The first column being red, second being green, third being blue. And we are already very, very close to the Trinitron layout. All we have to do is to find a way to introduce the masks, the small black borders between each column, and then a thicker border between each triad of colors. But despite that, the first one we're going to look at is the PC CRT. And as I mentioned before, I need to adjust the size of the pixels. The pixels need to be 3 times as wide as they are high. So I'm going to tie together these noodles and I'll drop a divide node onto the height variable because I'm going to reduce the height as opposed to increasing the width. I'll divide that height by 3. Let's have a look at the image output. We can see that the pixels are now rectangular, stretched horizontally, and we can split them into 3 squares, and into those squares will fit the dots of the Shadowmask layout. We're going to create those dots by splitting each pixel into 3 sections. I'll do that with another UV grid node. I'm going to use the normalized output of the first UV grid, preview the normalized output of this one, set the width to 1/3, the height to 1, and there we've got our squares, and we can use our normalized output to drive a UV distance node, and the output of that node goes into a math node with a function of less than and a threshold of 0.5. We've got our dots, and now we can incorporate those dots into this background mixing, this fading effect created by the CRT refresh node. A simple matter of a math node set to multiply, and the result of my less than goes into the bottom. Let's preview the output. We're looking good. We have to introduce that offset that I spoke of before, an offset of 1.5, exactly like a brick wall. So I'll turn on offset correct and introduce an offset of 0.5. There we go. Our pixels are correctly arranged. The dots are correctly arranged. Let's get a more suitable size. 1 divided by 480. There we have it. The original image is a little bit brighter, so I'll increase this brightness right here. Let's see what the refreshing looks like. Very, very good. There we go. PC CRT, and in fact, that's what I'm going to name this material. I'll click the shield to keep it, and I'm going to duplicate this one because the next material, the Trinitron material, as we've already seen, we're very close to being there already. We're going to keep most of what we have here, but we don't need this size adjustment, so I'll get rid of that. As a matter of fact, from here on, I'm going to control the pixel size with a single value because my pixels are always going to be square. So that'll be easier to manage. I'll control an X to delete this multiply node, but keep that noodle connection, and I'll get rid of the UV distance and the less than. Okay, again, I'll increase the pixel size so I can see what I'm doing. I don't need the offset for the Trinitron. There we go. Now, to create the borders, I'm going to take advantage of this UV grid node, which splits each of my pixels into 3 columns. And I'm going to use the standard output, which I'm going to separate. And now I can use the X component to drive a UV profile node. I'll copy the width variable from this UV grid into the size of the UV profile. And now I can use the space input to create the borders. There we go. This is the border between each individual column. I'll incorporate that into the refresh mask with a multiply node, just like before. And let's see what we've got. Looking good. Let's check the realistic pixel size and the refreshing. Okay, excellent. Bring the pixels back up because now I need to compress essentially each triad of columns, each group of red, green, and blue. I'm going to make them smaller in width, and I'm going to move them all slightly over to the left. I'm going to do that by manipulating this normalized output, which controls the second UV grid node. Actually, let me move all of these nodes together to keep things tidy. There we go. The third mask comes along because it's using the same normalized output. I'm going to drop in 2 vector math nodes. The first one is set to subtract 0, and the second to divide by 1. There we go. Now with the X input of the vector math subtract node, I can translate the groups left and right. And with the X of the divide, I can scale them in and out. So, to make the scaling match the translation, let's say, I have to scale them downwards by a value of 1 minus this value multiplied by 2. So if I use a fader node, for example, to control this variable here, I'll have to convert it into a vector first of all, combine x, y, z. The result of my factor goes into the x component of the separate x, y, z, and this goes into the bottom of the subtract. And now I can translate the groups with this fader here. This input will also need to be a vector, so I'm going to duplicate this combine node. I'll set all of the inputs to 1 and hook that up to the divide node. Now I need to multiply the result of my factor here by 2 and then subtract that result from 1. So that's factor multiplied by 2 and subtracted from 1. This result goes into the x of my combine. And now as I increase the space on the left, the group gets compressed to introduce the same space on the right and keep things nice and even. I'll drag that over just a little bit more. And I'm actually going to increase the size of the border between the columns. Something like that. Let's have a look at realistic pixels. Looking pretty darn good. That's the original image. That's the modified one, so I'm going to brighten it a little bit more. Let's see our flickering. Very cool. That's another one done. This one I'll call Trinitron CRT. Click the shield to keep it. And I'm going to bring up my PC CRT material again so I can duplicate that one. And we'll get to work on the TV CRT. So I'll give this material its name immediately. TV CRT. I'm going to increase the tile size, the pixel size. Remove the size manipulations, and in fact, once again, I'm going to use a single value node for both of the dimensions. Let's do that. Control and X, again, delete the UV distance and the less than again, and remove the offset again. There we go. Now, the Slotmask arrangement is really very, very similar to the Trinitron arrangement. The only difference is that we have to introduce capsule-shaped pixels as opposed to round pixels. And I'm going to achieve that with a UV brick node. So I'm going to use the standard output and copy the width and height settings. That's a third and 1 from the UV grid node. And now I can use the mask output. I'll introduce some space, and you can see that the mask is getting introduced around each individual column. I'm going to create the capsule shape by taking advantage of the edge function of this node. Something like that. And in order to make it a perfect capsule, I know that I have to make the edge size equal to half of the width of a column minus the space. So, again, if I use a fader node to control my space, I know that the maximum space is going to be half of the value of the width. That'll be 1/6 or half of a third. 1 divided by 6. Now I can use the value output to control the space, and I can neatly blend. Let me show you actually without the round corners. Neatly blend between maximum space and minimum space with no overrun or overspill. Now all I have to do is to subtract the result of this node, as I said, from half of the width. So I'll set it to subtract and enter 1/6. Subtract the fader result from that, and that will control my edge size. And now when I turn on round corners, we've got capsules as if by magic. And you can increase the size, and the edge updates automatically and keeps them perfectly round. So as before, to include this in the refresh mask, I'll use a math node and set it to multiply. And the mask result goes into the bottom. Let's see the color result. We're definitely looking good. See the flickering. And very quickly, let's have a look at 1 divided by 480. Very, very good. The final thing that we need to introduce into this model is the vertical offset. Now it's vertical in this case, so we can't take advantage of the offset built into UV Grid. We're going to have to do it a slightly different way. Here's how we're going to do it. I'm going to drag this value node over to the left so I can access that variable. I'll get a UV map and a UV grid. The result of this value node goes into the width, and I'm going to multiply that by 2. Now I'm going to have a look at the normalized output. I'll separate that normalized output and drop a math node onto the X component set to less than 0.5. And now I'm going to multiply the result of that less than by half of this value right here. So I'll divide that by 2, and that goes into the bottom of the multiply. And now this is the offset that I want to introduce vertically to my vector right here. So I'll drop on a vector math node, and I'll convert this value result into a vector with a converter, combine XYZ node. That goes into the Y, and the result of the combine goes into the bottom of the vector math. Let's have a look at our result. Looking good. We've definitely got the offset, but we need to remove that offset, or account for the offset, more to the point, after the UV grid node on this stepped output. So what I added here, I'm going to remove or subtract afterwards. The same result that I feed to the add node goes straight to the subtract, and there we have it. Now the image will not be distorted despite the offsetting. 1 divided by 480. Check the refreshing. Actually, let me increase the pixel size so we can make sure it's working correctly. Looks pretty good to me. Excellent. 1 divided by 480, and there's the flickering. TV CRT, already named, already saved, and ready to go. Okay, next up is my own slice of pie pixel shader, but just before I get to that, I want to take a second to say thank you to the 1,217 people who have subscribed to my channel on YouTube, and a very special thank you and shout out to everyone whose name is currently appearing on screen for reaching out in the comments section. Really, a very special thank you to each and every one of you. I really hope this YouTube journey starts to take off pretty soon. Now let's get back to Blender. I've got myself a fresh new material, and I've got a pixelated image set up here to begin with. So the first thing I'm going to do is to create a radial gradient for each pixel, in a very similar way to what we did with the UV distance node, if you remember how it was set up. I'm going to use the normalized output, and I'm going to separate the components. I'll use the X and the Y component, drop on a math node set to subtract to control the center point as far as the X is concerned, and we'll get its partner for the Y component. There we go. Now we'll need another math node. We're going to set the function to arctan2, and it's important that the Y component goes into the top and the X component goes into the bottom. Now we'll need another math node, and we're going to divide by pi multiplied by 2, or if you prefer by tau, T-A-U, just like that. And finally, another math node to add 0.5. And there you go, you got a radial gradient per pixel. Now let's wrap that up into a neat little utility node. Control and G as always. All we need to expose really are the center U and V values. That's what I'll call them, CU for center U and CV. And that's that node complete. We'll call it a UV angle. And we'll click the shield to keep it forever. This is going to be another useful one, I feel. Okay, so this is how this shader works. Essentially, we take the color output per pixel of our image, and we consider the red, green, and blue channels separately. We're going to add together all of these values to create a 100% color value, by which we can then divide the individual channels to discover the average, if you wish, or the percentage of the total color occupied by the red, green, or blue channels. So this is the result of red plus green plus blue. Let me just tidy these nodes up. I can now use a math node set to divide, and I'm going to divide the red channel by the total, and that gives me the percentage of the total color, which is made up by red. I'll do the same for the green channel. There we go. And that should be enough information for now. Next step, we're going to grab some value mask nodes, plug the result of our UV angle into the input, and I'm going to drag that up here. Now I need to mask out sections of this radial gradient based on the percentage of any of the given channels of the color red, green, or blue. You can see how this works. Actually, you'll see it better if I show you a single example of this. I'm going to set the pixel size to 1. So we're now looking at essentially one individual pixel. And you can see how the mask works right here. The full range of the radial gradient is 0 to 1. I can change the minimum and the maximum thanks to my value mask. So what I'm going to do is use one value mask node for the red, one for the green, and one for the blue. I'm going to set the minimum of the red mask to be 0 and the maximum to be the red value, very simply. There we go. That's the percentage of this color, which is made up by red. Now then, the mask for the green channel needs to begin at the end of the red. So I'll use the same variable I fed to the maximum here in the minimum here. And now the maximum value for the green section will be the green value plus the red value. So I'll do that very simply with a math node set to add. And that's going to be the maximum for this mask. Now very similarly to what I did here, the maximum for this node is the minimum for this node, and the same applies here. The maximum for this second node is the minimum for the third, so that goes into the min, and the maximum is a simple 1. So if this is my red slice, essentially, that's my green slice, and that's my blue slice. Looks like it makes sense, so let's compile it all into a color. That's my red, that's my green, and that's my blue. I'm going to tidy up a little bit here because this is getting very messy. I'll minimize the mask nodes, bring them in a little bit closer. And there we go. Now if I bring the pixel size back down to 0.01, something small for example, you can definitely see the image, but there is undeniably something wrong with the colors. Now that's because we have to incorporate the luminosity of the image. We'll do that. I'm going to drag the UV angle down a little bit so I can duplicate this node, drag it down, and then I'm going to switch the type to a converter, separate HSV node. Now I'm going to take this value and combine it into a color with a combine RGB, and this single value goes into all 3 of the channels. And now I'm going to multiply the result of this combine with the result of this one with a mix RGB set to multiply. Now that looks a lot better, doesn't it? Let's reduce the tile size a little bit more. 0.005. And realistic pixels, 1 divided by 480. And there we go. Next up, I'm going to incorporate the refreshing. And then I'll put this UV distance node to use. First, the refresh, CRT refresh. It shares the settings with the UV grid node. And we'll use that as before to drive a mix RGB with the image color in the bottom and the background in the top. This drives the mix factor. Drag up the intensity and manipulate the time. There's the flickering. Very, very good. You can leave the pixels as they are if you wish, but I took them one step further and made them round. It complements the pie chart idea much better, I feel. We'll do that as we have done before with the UV distance. The normalized output. The result of the distance goes into a math node set to less than 0.5, and there's your circle. As we did before, we'll multiply the fading result from the refresh node by the result of my circle mask, and there we go. Looks great on an image, looks even better in motion with a video or an image sequence. Let me show you. I'll use my usual image sequence of the made-up lady. So I'll need to scale the image because This is a 1920 by 1080 video, and I'm representing it on square geometry. So I'll use vector math nodes. One will be set to divide, and I'll divide the width by 1920 divided by 1080. There we go. And one more, we'll set that one to subtract and translate the image back into place. Activate cyclic and auto refresh on the image node. The settings are all wrong for this texture node. Okay, the frames are 197. Start frame will be 1. Offset will be 0. Thank you. Okay, let's try that again. Now we'll hit play and the image is working. Let's zoom in to see how these pixels behave. We can see them spinning around. We can see the slices growing and shrinking to accommodate for the color contribution. And it's all looking very, very good. To make the refreshing happen as I play the animation, I'll drop in a value node. Add a driver to give me the number of the current frame, hash frame. I'll supply that to a multiply node so I can control the speed of the refreshing. Plug it into the time of CRT refresh. Hit play and let's see how we do. Now, whole numbers or integers here really will never work for you. As you can see, you can't even see the flickering, and that's because the flickering is happening from top to bottom perfectly in the space of one frame, so we don't actually see the end of the gradient anywhere in the middle of the image. If I reduce this one or increase this one even by the tiniest amount, you start to see the flickering come in. There you go. I'm going to reduce the intensity a little bit. Go to default, and that's what we've got. Not bad at all. And I think that'll just about do it for this video. We've done astoundingly well. We've created 4 individual types, 4 different types of CRT screen shaders for animation, for still use images, videos, image sequences, and whatever else we can think of to use them for. Not to mention one of those methods being entirely original and somewhat one of a kind, but we won't linger on that. Thank you all very, very much for watching. I hope you enjoyed it and I hope you learned something, and I hope to see you in the next one. Take it easy.